Quantum mechanics, an overview. Quantum mechanics is a fundamental branch of physics that deals with the behavior of particles at the atomic and subatomic levels. It describes the physical properties of nature at small scales, where classical physics, Newtonian mechanics, fails to explain phenomena. Let's look at this topic from different perspectives. 1. The basics. At the heart of quantum mechanics is the concept that particles, like electrons and photons, behave both as particles and as waves. This duality is key to many quantum phenomena. Some essential principles include wave-particle duality. Matter and light exhibit both particle-like and wave-like properties. For example, light can behave as a wave in interference experiments, but shows particle behavior in the photoelectric effect. Superposition. A particle exists in all possible states until measured. This means, for instance, that an electron can be in multiple places at once, or an atom can be both decayed and undecayed, as in Schrödinger's cat thought experiment. Entanglement. Particles can become entangled, meaning the state of one particle is instantaneously connected to the state of another, no matter the distance separating them. This is sometimes referred to as spooky action at a distance, as coined by Einstein. Uncertainty principle. Introduced by Werner Heisenberg, this principle states that certain properties of particles, like position and momentum, cannot both be precisely measured at the same time. The more accurately you know one, the less accurately you can know the other. Quantum field theory, QFT. A more advanced perspective of quantum mechanics is quantum field theory, which extends the principles to account for the creation and annihilation of particles. This theory is crucial in explaining how particles interact and mediate forces like electromagnetism, the weak force, and the strong force. It forms the foundation for the Standard Model of particle physics, which explains 3 of the 4 fundamental forces in nature. Number 3. Interpretations of quantum mechanics. There are various interpretations of quantum mechanics that try to explain what these counterintuitive phenomena mean. Some of the most prominent are Copenhagen interpretation. The wave function, which describes probabilities of where a particle might be, collapses to a definite state only when observed. Until observation, the system exists in a superposition of all possible outcomes. Many worlds interpretation. Every possible outcome of a quantum measurement actually occurs, but in separate, parallel universes. For example, if you measure an electron's spin, in one universe it might be up, and in another, it's down. Pilot wave theory, Bohmian mechanics. This deterministic interpretation suggests that particles have definite positions at all times, guided by an underlying pilot wave. Unlike the probabilistic nature of standard quantum mechanics, Bohmian mechanics assumes an underlying reality. Applications of quantum mechanics. Quantum mechanics is essential for understanding and developing modern technologies, including semiconductors. Transistors, the building blocks of computers, rely on quantum mechanical principles to control the flow of electrons. Quantum computing. Unlike classical computers that use bits 0 or 1, quantum computers use quantum bits, qubits, which can be in a superposition of 0 and 1. This allows them to perform certain calculations much faster. Quantum cryptography. Quantum key distribution, QKD, ensures secure communication by leveraging the principles of quantum mechanics to detect any eavesdropping attempts. MRI machines. Magnetic resonance imaging relies on nuclear spin and the quantum mechanical behavior of atoms to generate detailed images of the human body. Future prospects of quantum mechanics. The future of quantum mechanics is expected to revolutionize various fields. Quantum computers. As quantum computing matures, it could drastically change industries, from cryptography and drug discovery to material science and AI. Companies like IBM, Google, and others are racing toward practical quantum computers. Quantum teleportation. Though not like teleportation in science fiction, quantum teleportation could allow for instantaneous transfer of information over vast distances via entanglement, potentially advancing quantum communication and the Internet. Unification with general relativity. One of the most significant challenges in physics is reconciling quantum mechanics with Einstein's theory of general relativity. The quest for a unified theory, sometimes called quantum gravity, is ongoing. Leading contenders include string theory and loop quantum gravity. Quantum biology. researchers are exploring how quantum effects might play a role in biological processes such as photosynthesis, bird navigation, and even consciousness, hinting at applications in biotechnology and medicine. Philosophical implications. Quantum mechanics challenges our classical intuitions about reality. The implications are profound. Nature of reality. What does it mean for particles to exist in superpositions or for multiple universes to exist? Quantum mechanics suggests that reality might be far stranger than our everyday experiences suggest. Observer effect. The role of the observer in collapsing the wave function has led to philosophical debates about consciousness, reality, and determinism. Does our observation create reality? Determinism versus free will. Quantum mechanics introduces indeterminism at a fundamental level, meaning certain events happen without any cause, such as radioactive decay. This has fueled debates about the nature of free will in the universe. Conclusion. Quantum mechanics has fundamentally changed how we view the universe, shifting away from the deterministic, clockwork world of classical physics to one governed by probability and uncertainty. As we continue to explore its mysteries, it holds immense potential for transforming technology, science, and our understanding of reality itself. The future of quantum mechanics lies at the cutting edge of physics, where discoveries may shape the next century as profoundly as it did the last.